What do quantization and pruning do to a model's epistemic structure beyond reducing flops and memory? Can we understand them not merely as engineering shortcuts, but as belief geometry events that alter the latent semantics of a model's neural genome? In this section, we pose a central research question: how do quantization and pruning reshape the model's internal belief geometry, specifically its spectral curvature, thermodynamic length, and belief vector field, when observed through the lens of neural DNA diagnostics? While prior work often focuses on compression-induced accuracy trade-offs, quantization noise, and robustness degradation, we explore a deeper hypothesis that such operations induce an irreversible semantic compression analogous to an entropy collapse, which distorts the model's epistemic manifold and reduces its ability to preserve instructional, cultural, or conceptual diversity in reasoning. By visualizing nDNA geometry before and after quantization or pruning, we aim to reveal whether these methods disproportionately collapse high-torsion belief zones, thereby flattening semantic diversity into brittle, low-entropy attractors. What you are seeing is a 3D plot of nDNA trajectories under 4-bit quantization for 9 culturally fine-tuned bases: Europe, North America, Australia, Latin America, Middle East, Asia, China, Africa, plus the llama base as reference. Axes are: kappa denotes spectral curvature, L denotes thermodynamic length, and the L denotes layer depth. Each colored path is the model's latent walk-through depth after quantization. The geometric story the plot tells. Across cultures, the paths contract and flatten as depth increases, thermodynamic length drops, the model spends less epistemic effort per layer, trajectories slide toward shorter L values, especially in the decision-making layers, mid-late 20s. Curvature compresses, the loops you see pre-compression are replaced by straighter, low upper arcs, distinct cultural basins pulled toward a common corridor, reducing representational richness and adaptability. Subtle kinks appear, bends no longer change smoothly with depth, the path snaps between regimes instead of turning continuously. Together, these changes erase fine-grained cultural separation and instructional nuance. The manifold has fewer bends to follow and less distance to explore. In mathematical terms, quantization maps a premodel M_pre to a compressed M_pruned, producing a fractured epistemic manifold characterized by 3 tests. Delta L at layer is negative across many layers. Translation: the change in thermodynamic length is negative. The student's path gets shorter layer by layer. This is loss of epistemic capacity. The network does less internal work before it answers. Change in kappa, post-pre, is not even smooth. Translation: curvature transitions are non-smooth. Instead of gently steering, the manifold has jumps and corners. That is a geometric fracture. Representational modes switch abruptly, hurting controllability and calibration. The divergence of the belief vector field is strongly positive in key regions. Translation: the divergence of the belief vector field becomes strongly positive. Belief flow fans out or dissipates. Intuitively, the alignment steering field loses conservation, semantic steerability weakens, so values and instructions no longer anchor the path. Consequences: a model that used to turn, think, and stay oriented now follows a shorter, straighter, less guided route. Conceptual agility drops, cultural calibration washes out, and robustness to fine-grained instructions or mild distribution shifts degrades. In nDNA terms, quantization pruning does not just cost a few points of accuracy, it resculpts the manifold, reducing the spectral bends, the thought budget or thermodynamics length, and the belief steering strength that together make reasoning rich and resilient. Now let us look at pruning through nDNA lens. What it really does to a model's mind. We ask, what is the latent cost of pruning on cognitive flexibility? Instead of only counting flops, we look at the model's epistemic manifold, its internal reasoning space, using 3 layer-wise readouts: curvature, length, and the belief vector field. What pruning does structurally. Introduce a sparsity knob S between 0 and 1. As you turn it up, pruning acts like a discontinuous operator on the landscape. It removes functional nodes and edges in the activation graph. Whole junctions or bridges disappear, creating geometric sparsity. It severs smooth trajectories, so bends are no longer continuously connected through depth. In math terms, curvature is no longer even smooth. It collapses representational subspaces, so lower dimensional, concept-affine, side valleys are squashed or merged. Mathematically, there are 3 diagnostics. Delta L is negative across layers. The thermodynamic length goes down, the path gets shorter. That is epistemic contraction. The network does less internal work before answering. Change in kappa, post-pre, is not even smooth. Curvature shows jumps and corners rather than gentle turns. This is a curvature discontinuity and a sign of structural fracture. The divergence of the belief field is strongly positive in key regions. Belief flow fans out or dissipates, the steering field loses conservation. This is semantic incoherence. Values and instructions no longer anchor the route reliably. The divergence as gradient.v equals the sum of layer-wise partial derivatives. Read it as, add up how much the belief flow is expanding along each hidden dimension. Large positive totals mean the steering guidance is leaking away. Topological interpretation. Pruning doesn't just thin weights, it can break homotopy, the deep connectivity of reasoning paths. In topology speak, the fundamental loop structure before and after pruning need not match. Intuitively, you create epistemic holes or semantic aneurysms in the manifold. Trails that once formed a coherent loop now dead-end or jump, so the model cannot smoothly traverse ideas that used to be connected. Practical consequences. Even moderate pruning produces a manifold that is shorter, kinked, and poorly steered. That shows up as reduced conceptual agility, brittle behavior on fine-grained instructions, cultural calibration that washes out, and degraded robustness under small distribution shifts. These failures are often invisible to simple loss metrics because surface accuracy can hold, while the internal geometry that supports generalization and value adherence collapses. Takeaway. Treat pruning as a geometric surgery on the model's mind. If you must prune, monitor the nDNA trio, kappa, length, and belief flow, and watch for 3 warning signs: delta L negative, non-smooth kappa changes, and large positive divergence of belief flow. When those appear together, pruning hasn't just sped up inference, it has damaged the manifold that makes reasoning stable, adaptable, and aligned. Let's discuss pruning setup. We study pruning on Llama 3.8b and read its effects on nDNA manifold. Prompts come from the civic, then we probe the moral, and we track the geometry. We apply 3 canonical pruning strategies, each grounded in the literature. First, attention head pruning. For every attention head, we compute an importance score as the average gradient norm of the cross-entropy loss with respect to that head, averaged over tokens. If that score falls below a small threshold, call it delta, we remove the head. Intuition, heads whose loss gradient is consistently tiny are treated as non-contributors to learning signals, so they are pruned. Second kind, MLP channel pruning. For each intermediate MLP neuron, we compute the Elvin norm, sum of absolute values of its activation weight vector. If this magnitude is smaller than a small threshold, call it epsilon, we remove that channel. Intuition, low magnitude channels contribute weakly across inputs and can be dropped with minimal immediate loss impact. The third kind of pruning we applied is transformer layer pruning. For each full transformer block, we measure a Fisher-style score, the expected value of the squared gradient of the cross-entropy loss with respect to that layer's parameters. If this expected square falls below a cutoff, call it tau, we drop the entire block. Intuition, when the model's loss barely changes as you move that layer's weights, the layer is judged non-critical and can be removed. What we see in terms of geometric fingerprints for each kind of pruning. Head pruning mainly disrupts routing. Expect local drops in belief steering strength and sharper, sometimes non-smooth turns where heads used to stabilize attention. Mid-layer kappa can become spiky and late-layer steering can fade. MLP channel pruning narrows the feature palette. Curvature shrinks steadily and thermodynamic length contracts. Cultural separations in latent space blur because expressive channels for fine concepts disappear. Layer pruning changes the model's depth budget. This has the largest macro effect. Length shortens across many layers, curvature transitions lose smoothness, and the belief field weakens broadly. Classic signs of a fractured manifold rather than a mere size reduction. How to read results you'll see later. If you hear delta L negative, think less thought per layer. If you hear change in kappa is not even smooth, think kinks and mode switches instead of gentle turns. If you hear divergence of the belief field is strongly positive, think the steering flow is leaking, values and instructions no longer anchor the path. This setup lets us compare pruning strategies not only by speed up and accuracy but by manifold integrity, whether the model still turns, thinks, and stays oriented after we cut. Let's see how each pruning regime, heads, channels, and whole layers, imprints a distinct scar pattern on the cultural nDNA trajectories. Llama, pruning scars at a glance. Heads, orange knocks out routing edges mid-late layers lose path length and turning power. small kinks appear. Translation: less internal work and weaker turning power exactly where global attention stitches views together. Channels: green narrows the feature palette smooth, global shortening and steady curvature flattening. Translation: fewer features to recruit and lower semantic resolution, so answers hold but nuance and fine control fade. Layers: red deletes a depth segment step change in curvature with the largest local disruption. Translation: a depth hole in the stack, long-range coordination breaks, reasoning skips a step, and decisions become brittle on long horizons. Bottom line: heads hurt stitching, channels erode detail, layers create a structural gap, and all three shorten the reasoning path. Africa pruning scars at a glance. Heads: orange knocks out routing edges, mild mid-late shortening and small kinks relative to the base. Translation: less internal work and weaker turning power exactly where global attention stitches views together. Channels: green narrows the feature palette smooth, global shortening with a steady flattening of curvature across depth. Translation: fewer features to recruit and lower semantic resolution, so answers hold but nuance and fine control fade. Layers: red deletes a depth segment, a visible step in curvature around the removed block with the largest local disruption. Translation: a depth hole in the stack, long-range coordination breaks, reasoning skips a step, and decisions become brittle on long horizons. Bottom line: heads hurt stitching, channels erode detail, layers create a structural gap, and all three shorten the reasoning path in the African nDNA. Asia, pruning scars at a glance. Attention head pruning in, orange removing whole attention heads, severes routing edges. Mid to late layers show a shorter path, lower thermodynamic length, and jagged curvature with small oscillatory spikes as the stack tries to reroute. Translation: less internal work and weaker turning power exactly where global attention normally stitches views together. MLP channel pruning in, green deleting feed forward, MLP, channels narrows the feature palette. The trajectory shortens smoothly and curvature flattens across depth. Translation: fewer recruitable features and lower semantic resolution, answers may hold, but nuance and fine control fade. Transformer layer pruning in, red dropping an entire transformer block removes a chunk of depth. You see step-like jumps in curvature and a local trough in length. Translation: a depth hole in the stack, long-range coordination breaks, reasoning skips a step, and decisions become brittle on long horizons. Bottom line: attention head pruning harms stitching, MLP channel pruning erodes detail, and transformer layer pruning creates a structural gap, and all three shorten the reasoning path. Now, let's observe how pruning plays out in the Australia, China, and Europe-tuned models. Australia, pruning scars at a glance. Attention head pruning in orange, removing whole attention heads, severes routing edges. You see an early drop in thermodynamic length around layers 22 to 24, with mostly smooth curvature and a few small kinks as the stack tries to reroute. Translation: the global aggregator loses clean handoffs, so the model starts coasting, it keeps direction but with less thrust, turns become wide and lazy rather than crisp. MLP channel pruning in green, deleting feed-forward MLP channels narrows the feature palette. Length contracts from -21 to -28, steepest -23-26, while curvature gently flattens from -22 to -30. Translation: the palette fades to pastels, answers still arrive, but with fewer strokes, micro-adjustments and fine shading drop out. Transformer layer pruning in red, dropping an entire transformer block removes a chunk of depth. There's a local trough in length centered near layer -26, with a curvature step -25-27 and length recovery by -28-29. Translation: a missing rung in the ladder, planning hesitates at that depth, so multi-step reasoning stalls or jumps instead of flowing. Bottom line: Australia's signature injury is early loss of momentum. The reasoning path shortens early and hard. Attention head pruning induces coasting, MLP channel pruning drains fine detail, and transformer layer pruning opens a depth gap. All three compress the manifold and cut the model's effective depth budget. China, pruning scars at a glance. Attention head pruning in orange. Removing whole attention heads cuts routing edges. The biggest impact sits in the mid-stack. From roughly layers 21 to 25, the thermodynamic path shortens and curvature shows spiky kinks, often near 24 and 27, as residual routes try to restitch context. Translation: less internal work and choppier turning power right where global attention normally binds long-range cues. MLP channel pruning in green. Dropping feed-forward channels narrows the feature palette. The trajectory contracts almost linearly from about layer 21 to 29. The curvature envelope shifts downward with a gentle sawtooth at 24, 26, 28, a signature of residuals compensating for missing features. Translation: fewer recruitable descriptors and lower semantic resolution. Answers hold, but subtle distinctions and fine steering fade. Transformer layer pruning in red. Removing an entire transformer block carves out a depth segment. You see a step-like kink in curvature centered near the excised block, often around layer 25, plus a local trough in length across 24 to 26 as the stack skips a reasoning step. Translation: a depth hole breaks long-range coordination. Planning across multiple hops becomes brittle. Bottom line: head pruning disrupts stitching, channel pruning erodes detail, and layer pruning punches a structural gap. Each one shortens the reasoning path and weakens turning power, with the mid-stack, about 23 to 27, emerging as the most sensitive zone for this China-tuned lineage. Europe, pruning scars at a glance. Attention head pruning in orange. Removing whole attention heads severs routing edges. The mid-stack, layers tilde 22-27, shows a steady shortening of the thermodynamic path with small stair-step kinks in curvature, often near 23 and 26, as the model rethreads context through fewer heads. Translation: fewer long context stitches, discourse binding becomes less stable, so multifact aggregation can wobble. MLP channel pruning in green. Dropping feed-forward channels thins the feature palette. The trajectory contracts nearly linearly from tilde 21 to 29, while curvature gently flattens with light sawtooth nicks at 24, 26, 28 from residuals sharing load. Translation: reduced semantic resolution, nuanced qualifiers and soft distinctions are the first to fade, even when answers remain correct. Transformer layer pruning in red. Removing an entire transformer block creates a depth gap. You see a sharp curvature kink around the excised block, often tilde 25-26, and a local trough in length across tilde 24-27, marking a skipped reasoning hop. Translation: a depth hole breaks long-range coordination. Stepwise chains are more brittle on longer horizons. Bottom line: attention head pruning weakens discourse stitching, MLP channel pruning erodes fine-grained detail, and transformer layer pruning opens a structural gap. Each shortens the reasoning path with a particularly sensitive band in the European stack around layers 23 to 27. Now, let's examine how pruning scars nDNA manifolds across the Latin America, Middle East, and North America variants. Latin America, pruning scars at a glance. Attention head pruning in orange. Removing whole attention heads severs routing edges. In the Latin American stack, the largest shock lands in mid-late depth, layers tilde 24-27 thermodynamic length dips and curvature shows wide, zigzag swings, bigger than other cases, as if the model is overcompensating with the remaining heads. Translation: discourse stitching oscillates, evidence gets braided, then unbraided, so multi-source answers can feel confident but uneven. MLP channel pruning in green. Dropping feed-forward channels thins the feature palette. The trajectory contracts steadily from tilde 22 to 29, yet curvature exhibits alternating ridges at 23, 25, 27, 29, suggesting residual pathways taking turns shouldering load. Translation: expressive color is lost. The model still lands the fact, but hedges, qualifiers, and cultural nuance are smoothed out. Transformer layer pruning in red. Excising a whole block creates a depth gap. You see a clear kink around the removed band, typically tilde 25-26, and a shallow trough in length across tilde 24-27, followed by only partial recovery late. Translation: a skipped reasoning hop, long-range coordination weakens, so step-by-step explanations get brittle over longer chains. Bottom line: attention head pruning injects oscillatory stitching, MLP channel pruning sands away nuance, and transformer layer pruning opens a structural gap. All three shorten the reasoning path, with a particularly sensitive band in layers 24 to 27 for this cultural variant. Middle East, pruning scars at a glance. Attention head pruning in orange. Removing whole attention heads severs routing edges. The trajectory shows a compressed path from layers tilde 23-27 with curvature jolts near tilde 25, as the stack retries alternative routes. Translation: cross-reference stitching wobbles, threads that tie scripture, precedent, and facts together fray, so the model alternates between assertive claims and walkbacks. MLP channel pruning in green. Dropping feed-forward channels thins the feature palette. Length shrinks steadily from tilde 22 up to 29, while curvature forms a sawtooth pattern, peaks and dips at tilde 23, 25, 27, signatures of remaining motifs taking turns to carry meaning. Translation, descriptive richness and valular then framing fade. Answers become more literal and less capable of shading intent or context. Transformer layer pruning in red. Excising an entire block opens a depth gap. You see a clear kink around the removed band, typically tilde 25, 26, and a local trough in length across tilde 24, 27, with only partial recovery late. Translation, a skipped reasoning hop, multi-step justifications, example, law ethics practice, truncate, and long horizon arguments become brittle. Bottom line, attention head pruning destabilizes narrative stitching, MLP channel pruning sands away expressive nuance, and transformer layer pruning creates a structural gap. All three shorten the reasoning path, with a sensitive band in layers 23 to 27 for this cultural variant. North America, pruning scars at a glance. Attention head pruning in orange. Removing whole attention heads cuts global routing edges. The nDNA trace shows shorter thermodynamic length in layers 22 to 27 and small curvature dips near layers 24 and 26 as the model tries to reroute. Translation, less internal coordination and weaker zoom-out control. Long context stitching becomes thinner and intermittent. MLP channel pruning in green. Dropping feed-forward channels thins the feature basis. Length contracts steadily from layers 21 to 29, and curvature flattens in a gentle staircase. Translation, fewer descriptive features to recruit. Answers often stay correct but lose nuance and policy shading, so reasoning sounds more literal. Transformer layer pruning in red. Removing a full block creates a depth gap. A clear kink appears near the removed band, usually around layers 25 or 26. Length shows a local trough across layers 24 to 27, then a mild rebound later. Translation, a skipped reasoning hop, chains of thought compress, so conclusions arrive faster but with shallower justification. Bottom line, head pruning reduces stitching, channel pruning reduces nuance, and layer pruning creates a structural gap. All three shorten the internal reasoning path, with the layers 22 to 27 corridor especially sensitive in this model. In the next two quick videos, we'll build intuition for compression through the nDNA lens. In clip 1, quantization as a genome-wide hypermorph. Watch the 3-D nDNA path lose bend, curvature flattens, shorten, thermodynamic length drops, and show a softer, narrower steering field. The model often keeps the same answers, but its internal route becomes shorter, straighter, and less guided. In clip 2, pruning as a chromosomal segment deletion. Look for local fractures. Attention head pruning knocks out long-range stitching. Small kinks mid-late stack. MLP channel pruning thins the feature palette. Smooth shortening and flattening. And whole layer pruning creates a visible depth hole, step change, and a local trough. The biological analogy takeaway. Quantization turns the volume down everywhere. Pruning removes wiring. Both reduce epistemic richness unless we compress with geometry in mind. Up next is a primer on chromosomal alterations, big edits to our DNA.
Alterations, also known as chromosomal mutations or abnormalities, are changes in the structure or number of chromosomes in an organism's cells. There are several types of chromosomal alterations. 1. Deletions. These involve the loss of a portion of a chromosome, resulting in missing genetic material. 2. Duplications. In this type of alteration, a segment of a chromosome is duplicated, potentially causing an increase in gene dosage and altering an organism's traits. 3. Inversions. An inversion occurs when a chromosome segment is flipped in orientation. 4. Translocations. Translocations involve the movement of a chromosome segment to a non-homologous chromosome. 5. Aneuploidy. This is the gain or loss of entire chromosomes, leading to an abnormal chromosome number, as seen in conditions like Down syndrome, trisomy 21.
How chromosomal deletions impact genetic diseases. In the realm of genetics, deletion refers to an intriguing chromosomal anomaly that results in the loss of genetic material. This loss can give rise to a wide array of genetic conditions and diseases. It's a bit like removing a chapter from a book. Suddenly, the whole story can change. Over the years, advancements in genomic technologies have allowed us to not only identify these deletions with precision, but also to understand their character and behavior. This has significantly broadened our understanding of how these deletions impact our genetic makeup and their role in disease development. It's like having a magnifying glass that allows us to closely examine and comprehend the molecular mechanisms and the functional impacts of these deletions. As we continue to explore this fascinating world of genetics, let's delve deeper into the mechanisms that lead to these deletions. A myriad of mechanisms contribute to deletion formation. This vibrant tapestry woven by our genetic code is not infallible, and sometimes a thread goes missing. A deletion occurs. One of the primary culprits behind deletions are DNA double-strand breaks, or DSBs. These are like fractures in the genetic material, occurring spontaneously during the process of DNA replication or induced by external factors such as radiation or chemicals. Now, our bodies have complex machinery for repairing these breaks. Two key players in this process are non-homologous end joining, or NHEJ, and homologous recombination, or HR. Picture NHEJ as a quick fix. It's like taping the broken ends together, albeit sometimes imperfectly. On the other hand, HR is more like a skilled craftsman, using a sister chromatid as a blueprint to accurately mend the break. However, when these repair systems falter, the result can be a loss of genetic material, leading to the formation of deletions. Imagine it as a sentence in a book where suddenly a chunk of words go missing, altering the meaning of the sentence. That's exactly what happens to our genetic code. Moreover, our environment and lifestyle play a significant role in this process. Exposure to certain environmental factors and mutagens can cause DNA damage, thereby increasing the likelihood of deletions. It's akin to living in a city with a high crime rate, where the chances of being robbed are higher. The interplay between these biological and environmental factors sets the stage for deletion formation. It's a dance, a delicate balance of creation and destruction, repair and damage. And when this balance is disrupted, deletions occur, leaving an indelible mark on our genetic code. And so the mechanisms behind deletions are multifaceted and complex, involving both our genetic machinery and the world around us. It's a testament to the intricate and dynamic nature of our genetic code. Yet these mechanisms in turn have profound effects on chromosomal function, altering the symphony of life in ways both subtle and profound. Deletions can significantly alter chromosomal function and gene expression. When essential genetic material is lost to deletions, the repercussions are far-reaching. The normal activities of a cell, the smallest unit of life, can be disrupted. This disruption can, in turn, lead to an array of developmental anomalies. It's like removing an important cog from a well-oiled machine. The entire system grapples with the sudden change, trying to adapt and compensate, but the result is often a breakdown. This breakdown is not just confined to a single cell. It can manifest in the form of cognitive impairments, affecting an individual's ability to think, learn, and remember. Deletions can also create a susceptibility to various diseases. Imagine a fortress with a compromised wall. That's what a cell with a deletion is like, vulnerable and open to invasions by disease-causing agents, including the dreaded cancer. Now, let's delve a bit into the concept of haploinsufficiency. It's a term that sounds complex, but it essentially means that a single functional copy of a gene is not enough to maintain normal function. When deletions occur, they can lead to haploinsufficiency. Picture a pair of workers lifting a heavy load. If one worker disappears, the remaining one struggles to lift the load on his own. Similarly, when one copy of a gene is deleted, the remaining copy may not be sufficient to carry out the gene's function, leading to various phenotypic manifestations. These manifestations are often associated with the disorder related to that particular gene. In essence, deletions are like missing pieces in the intricate puzzle of life. Their absence disrupts the beautiful picture that our genetic material paints, leading to a cascade of effects that impact our health and development. But there's a silver lining to this cloud. The better we understand these impacts, the more effectively we can devise strategies to combat them. Understanding these impacts opens up therapeutic avenues. It's a testament to the power of knowledge and our relentless pursuit of understanding the world within us. The knowledge of deletion formation mechanisms holds great therapeutic promise. This statement holds the key to our hopes for a future where genetic disorders caused by deletions are no longer insurmountable challenges. Let's consider some of the potential interventions on the horizon. One of these is gene therapy, a medical field that has already made a significant impact in treating a variety of diseases. This approach involves introducing, removing, or altering genetic material within a patient's cells to mitigate or cure disease. For disorders caused by deletions, gene therapy could potentially replace the missing genetic material, restoring normal function. Another promising frontier is gene editing technologies, like the revolutionary CRISPR-Cas9 system. This tool allows scientists to edit parts of the genome by adding, removing, or altering sections of the DNA sequence. Think of it as a molecular pair of scissors that can snip out the problematic parts and replace them with healthy ones. In the context of deletions, this could mean precisely targeting and correcting the deleted segment, potentially reversing the effects of the chromosomal abnormality. But it's not just about correcting deletions after they've occurred. There are also strategies aimed at preventing or repairing DNA damage in the first place. For instance, DNA repair inhibitors can be used to enhance the cell's natural defense mechanisms against DNA damage, thereby reducing the likelihood of deletions. Similarly, radioprotective agents can shield cells from the harmful effects of radiation, one of the environmental factors that can induce deletions. These are just a few examples of how our growing understanding of deletions can be harnessed for therapeutic purposes. But as with all scientific endeavors, there are still many unanswered questions and challenges to overcome. Continued research into deletions and their role in disease pathogenesis is set to revolutionize the treatment of genetic disorders. Deletions, once an elusive and misunderstood aspect of our genome, are now at the forefront of genetic research, promising to unlock new ways to prevent, manage, and treat a wide range of diseases. The future of genetics, it seems, is not just about understanding our DNA, but also about learning to rewrite it.
Let's dig a bit deeper using a biology lens, treating the model like a genome. We'll see quantization as a genome-wide hypermorph and pruning as a chromosomal deletion, then read their footprints with nDNA. We ask how low-bit uniform quantization reshapes a transformer's epistemic manifold when we read it with the nDNA trio across depth. Quantization does not cut out modules, it reduces resolution everywhere. The model may give the same answers, but the internal geometry that supports adaptation becomes shorter, straighter, and less guided. What quantization does, operator view take a weight tensor W in some layer or block. In b-bit uniform quantization, we map W to a quantized tensor, W hat, by first choosing a scale S, read as alpha divided by 2 to the power b minus 1, then replacing each weight by S times round of W divided by S. You can think of W hat as W plus small zero mean noise whose variance grows with S squared, so coarser steps add more noise. Second-order schemes like GPTQ pick S to minimize a local quadratic proxy of the layer loss, but the core effect remains the same. Resolution is lowered along many directions at once. YL, kappa, and the belief field move, information geometry view. Let J sub L be the Jacobian from layer L-1 to layer L, and let F sub L be the Fisher matrix, the expected outer product of the score, that is, the gradient of log probability. Quantization perturbs the Jacobian chain, so sensitivity along the principal directions shrinks. In practice, we observe three things. First, L sub L contracts, which means the path performs less epistemic work. Second, kappa flattens, which means fine bends are damped. Third, the magnitude of the belief vector we superscript C at layer L weakens and aligns into a narrower cone, which means value or instruction steering loses spread. Chromosome-level analogy, clear mapping weights behave like loci, layers or blocks behave like regulatory neighborhoods, TADs, scales and zero points behave like chromatin accessibility. Quantization is effectively a genome-wide hypermorph. Every locus persists but its dynamic range is clipped, and small variations fall below the noise floor. Nothing is deleted, it is a resolution squeeze similar to mild chromatin compaction. Intuitively, the melody, task behavior, stays recognizable, but the musical dynamics, crescendo, rupto, microtiming, are flattened. In nDNA terms, kappa goes down, L goes down, and the belief steering cone tightens because the belief vector magnitude decreases. Control and robustness, intuition first, math beneath depth behaves like a dynamical system that transports representations forward. The controllability gramian at layer L tells us how many directions are reachable with finite energy. Quantization squeezes the singular spectrum of the Jacobian, so the total controllable power falls. Sharp turns become harder, the traversable path shortens, and value or instruction alignment exerts weaker guidance. Off-distribution adaptation, turning toward novel or rare evidence, degrades in proportion to the principal Fisher directions that are lost. Takeaway: quantization is not a benign size change, it is a resolution transform. Through the nDNA lens, the manifold becomes shorter, L decreases, straighter, kappa decreases, and less guided, the belief vector magnitude decreases and becomes more collinear. The phenotype may survive, but the epistemic richness that supports agility and robustness is pared back. Pruning is not a tidy trim. It behaves like removing a chromosomal segment. Entire sets of co-adapted functions disappear together, which breaks long-range coordination. When we read the model with nDNA, the latent manifold that carries reasoning becomes shorter, more kinked, and less well-stared. In nDNA terms, this shows up as three coordinated shifts by depth: thermodynamic length L sub L contracts, spectral curvature kappa sub L either flattens or develops sharp corners, and the magnitude of the belief vector V superscript C sub L weakens or leaks in unintended directions. What pruning does in simple language: think of each layer as a map with a Jacobian that transports representations forward. Pruning composes that map with a projection that removes whole coordinates or routes. Doing so lowers the rank of the transport, squeezes its singular values, and therefore cuts Fisher information and controllability. That is why the nDNA trio, curvature, length, and belief field strength, drop together. Chromosome-level analogy. Let's understand how the pieces line up. Times heads, channels, and layers correspond to genes and modules. Times blocks correspond to regulatory neighborhoods, the places where crosstalk is organized. Times skip or attention routes act like enhancer-promoter links. Under this mapping, pruning resembles a copy number deletion. You delete a contiguous module, expression dosage falls, insulation collapses, and the compensating cross-couplings that used to stabilize behavior fail. How each regime leaves a distinct nDNA fingerprint. Attention head pruning is more or less a route deletion. Criterion in practice: remove heads with low gradient importance. Graphically, heads are edges in a routing multigraph. Deleting edges reduces algebraic connectivity, so global coordination weakens. In nDNA, you see mid-layer curvature become spiky, non-smooth turns appear because the stack is trying to reroute. L sub L shows local drops where stabilizing heads were removed. The belief field magnitude dips near those layers, revealing steering holes where guidance used to be supplied by now missing heads. Translation: you lose stitching power. Long-distance context is harder to weave. MLP channel pruning is basically a feature palette deletion. Criterion in practice: magnitude or lasso-style scoring of channel weights. Prune the smallest set. Mathematically, this multiplies the layer by a projector, which drops small singular values of the Jacobian and shrinks the Fisher energy carried by that layer. nDNA shows a smooth but persistent pattern. Kappa sub L trends down, L sub L trends down across the pruned block, and cultural separations blur because the feature palette is thinner. Translation: fewer recruitable features, lower semantic resolution. Answers may hold, but nuance and calibration fade. Transformer layer pruning resembles a block or segment deletion. Criterion in practice: low Fisher or gradient score at the block level. Removing a whole block changes the depth connection discontinuously. Holonomy and torsion jump, curvature becomes piecewise with visible kinks, reasoning paths skip a step. Globally, L contracts across many layers, kappa shows step changes, the belief field either weakens broadly or fans out, steering leakage, as the model searches for alternate routes. Translation: a structural gap appears in the stack, long horizon coordination breaks. Then the question is why robustness may suffers. Let's understand from the lens of information geometry and control. With Fisher matrix and controllability Gramian as guides, pruning reduces the reachable subspace. Small singular modes vanish and the sum of controllable directions falls. Intuitively, fewer well-conditioned directions means harder turns, lower curvature control, a shorter path to think, lower L, and a weaker compass for value or instruction alignment, smaller belief vector magnitude, often less well-aligned. Off-distribution adaptation degrades even if in-distribution accuracy looks fine, because the principal directions that once supported detours and recovery are missing. Bottom line: pruning deletes structure. Heads delete routes and hurt stitching, channels delete features and erode detail, layers delete depth and create a gap. All three shrink thermodynamic length, flatten or fracture curvature, and weaken the belief steering field, leaving a shorter, kinkier, and less steerable manifold. Please refer to the book and the website for further details.